Today, lesson 43B, unit rates and tables. So we continue with our theme in this unit of the discussion of unit rates. But today we bring in something that I referred to at the very end of yesterday's lesson, and that's this idea of proportionality. And so today we bring in this idea of constant of proportionality. All right, so let's go ahead and get started. Background knowledge from the two previous days. Remember, a unit rate is a rate that compares quantities in different units and has a denominator of 1. And when we're finding the unit rate, we're trying to figure out how many of y per 1 of x, or how many of one thing per 1 of another thing. Here was a problem we did yesterday, and I had you find the unit rate both directions. In other words, with the given rate there, you had to find first how many windows per hour she could clean. And so that would be 5/8 of a window divided by 1/10 of an hour. And that gives us 25/4 windows per hour for that unit rate. And then the other direction, how many hours per window? We would find that by dividing 1/10 of an hour divided by 5/8 of a window. And that gave us 4/25 of an hour per window. Okay? Sometimes the unit rate makes sense in both directions, sometimes not. And then the last couple of days we've been comparing the difference between ratio. There's a lot of similarities here, but the difference between a ratio, a rate, and a unit rate. For ratios, we typically reduce to simplify, and we don't need the units. When we have a rate, which is a form of a ratio, we have things where we have to include units like 300 miles for 5 hours, and that's usually not simplified, because when it is simplified, it's now a unit rate. And taking that same rate and converting it to a unit rate, we end up with 60 miles per hour. In a unit rate, the denominator, once again, needs to be 1. We always write the units. We divide to simplify. And as we've talked about several different times, money usually goes on top. That's not always the case, but it usually is. All right, so let's start at number 1. It took Derek 7.5 hours to drive 220 miles. Well, from that one sentence, there are 3 things that we have there. First of all, we have a ratio, and then we have a rate, and then from that, we're going to try and find the unit rate. But before we even get into that, we need to think about, and I've been alluding to this the last couple of days, of trying to figure out which unit rate makes the most sense. And a lot of times, it's what you've heard before in life. So in this problem, which makes more sense? Hours per mile or miles per hour? Yeah, you've heard miles per hour a lot. You've probably never heard hours per mile, though. So it is miles per hour that we're going to use to find the unit rate and to set up our ratio and our rate. So here's what we have. We have a ratio, we have a rate, and we're going to find the unit rate. So here's where you need to start filling things in. The ratio found within that problem, since we decided we're going to find miles per hour, would be 220 over 7.5. And that, given within the problem, is not simplified. And then from that ratio, we have the given rate within the problem, which is 220 miles for 7.5 hours. And in the first 3 problems, I'm having you write all 3 of these things down. Okay? Now, from that rate, we can find the unit rate. Now, I'm going to do the math for you here. So to find the unit rate, 220 divided by 7.5, so that's 29 1/3 miles per hour. 29 1/3 miles per hour. That's the unit rate for this situation. Now, the unit rate is a very powerful thing because we can find lots of things from that unit rate, and that's the exact reason why we find it. Okay? Now, once again, I already kind of mentioned this, but the ratio there is not simplified, the rate is not simplified, but the unit rate is simplified. Okay? So now that we found the unit rate, we know that Derek travels 29 1/3 miles for every single hour. Each hour he travels another 29 1/3 hours. So here we have this table. And so we can go ahead and fill in the first part there. We know for 1 hour he can travel 29 1/3 miles. Now we're going to fill in some other parts of that table. So what we know now is this. We should be able to figure out, since we know the unit rate, we should be able to figure out how far he travels in 2 hours. How would we figure that out? Yeah.
Multiply 29 and 1/3 by 2.
Yeah, because that unit rate is powerful. For every hour, he travels 29 and 1/3. So for 2 hours, 29 and 1/3 times 2. That's 58 and 2/3. For the first problem here, I'm going to do all the math for you, okay? But I'm just showing you how I get that. And of course, for 3 hours, it would be 29 and 1/3 times 3, because for every single hour, he travels 29 and 1/3 hours. That's 88 miles. And I may have said that incorrectly just a second ago. 29 and 1/3 miles for every single hour. Now, for 7.5 hours, of course, we would multiply 29 and 1/3 times 7.5. And so in 7.5 hours, he could travel, if he traveled at the same rate, he could travel 220 miles. So once we knew the unit rate, we could find any number of hours. For any number of hours, we could find out how far he traveled. And the reason is because we know that the unit rate is 29 and 1/3 miles per hour. And so I know you've got some areas that you're supposed to be filling in your notes right there. That's the unit rate. And the number part, the numeric part of that unit rate is something that we call the constant of proportionality. And we're going to say that phrase probably 5,000 times over the next 2 weeks. Constant of proportionality. It's the numeric part of the unit rate. Now, it's usually at this point some people are like, what in the world does that mean? Constant of proportionality. Well, here's what it means. It is, or can be thought of as, the constant multiplier. It's the number that we are using to multiply each time to figure out what we're trying to figure out. And in this case, the constant multiplier is 29 and 1/3, because depending on how many hours he traveled, we would multiply that by 29 and 1/3 every single time. So if I wanted to figure out how far he traveled for 25 hours, I would do the same thing. The constant multiplier is 29 and 1/3. So for 1 hour, 1 times 29 and 1/3 is 29 and 1/3. For 2 hours, multiply by 29 and 1/3. For 3 hours, multiply by 29 and 1/3. For 7.5 hours, same thing. For 25 hours, same thing. So the constant of proportionality can be thought of as a constant or same multiplier. It's the number you're multiplying by every single time, as I just showed you right there. Okay? And we get that, or we derive that from finding the unit rate. Okay, so let's go to number 2. Alexia earned $47.95 for 7 hours of work. Which makes more sense, dollars per hour or hours per dollar? Yeah, and that's another term you've heard over and over and over again. So that's when we set up our ratio and set up our rate and set up our unit rate, that's what we're finding, dollars per hour. So the ratio, of course, would be 47.95 over 7. The rate would be $47.95 for 7 hours. I'm going to let you take it from there. Find the unit rate. To find the unit rate, 47.95 divided by 7, and that leads us to a unit rate, and that's what I heard from the majority of you, $6.85 per hour. And once again, the unit rate is very powerful because now we can find any piece of information based on what we're dealing with here, because we know that for every single hour, Alexia earns $6.85. So now let's set up our table. And we have that. We can fill in for 1 hour, because for 1 hour he earns $6, or she earns $6.85. And I kind of have the things out of order here, so I'll let you fill in the rest of the numbers in your table. Can you go ahead and fill them in? It'd be 1, 2, 3, 7.5, and then you're going to add another column, 25. So the hours going across would be 1, 2, 3, 7.5, and 25. I'm going to give you a couple of minutes to finish filling in that table. Our unit rate was $6.85 for every hour. So that means if Alexia worked 2 hours, 6.85 times 2, because that is the constant multiplier, that would give us $13.70. For 3 hours, 6.85 times 3 is $20.55. For 7 hours, since the constant multiplier is 6.85 times 7, that's $47.95. And so, before we do the last one there,
You said 7.5.
what did I say?
7.5.
Okay, sorry. $47.95. Is that where I said it incorrectly?
Yeah.
Okay, regardless, it's up on the screen, right? So the unit rate, once again, is $6.85. The constant of proportionality, which is the constant multiplier, is 6.85. It's just the numeric part. We don't need units. We don't need anything. We don't need a dollar symbol in this case or anything like that. And so, of course, if we wanted to add another column on there, 25 hours, that would mean Alexia earned 6.85 times 25, which is $171.25 or $171.25. Making sure I say it correctly that time. Okay, number 3. Do that one all the way through. In 2/3 of a day, you paint 4 2/3 rooms. The unit rate that makes the most sense is rooms per day. And so the ratio given within the problem is 4 2/3 over 3/5. The rate given within the problem is 4 2/3 days for 4 2/3 rooms for 3/5 of a day. And then we convert that to a unit rate by dividing. So that's 7 7/9. I know some of you left it as 70 over 9. Same thing. Rooms per day. And so now we can figure out or fill in 1 day on our table because you paint 7 7/9 of a room, or 7 7/9 rooms per day. So for 2 days, we multiply that by 2, and of course 7 7/9 rooms per day is our unit rate, but only the 7 7/9 is our constant of proportionality. And make sure you fill that in for every single one of these problems, okay? So for 2 days, multiply by 2 because that's the constant multiplier. That's 15 5/9 rooms. For 3 days, multiply by the constant multiplier. That's 29 1/3 rooms. And for 6/5 days, multiply by that, and that's 9 1/3 rooms. Now I have a question for you, and that's because as we go through these idea of tables representing situations, sometimes we don't even need to use the constant multiplier. So I have a question for you, and that's this. Is there an easier way that we could have found that value right there rather than multiplying 6/5 by 7 7/9?
I added 3/5 times 7 over 7/9, and then I added it to the,
To itself?
yeah,
Yeah. Why did you do that?
because it was the same denominator, so we could just add it on.
So you're having trouble explaining it. I think what you mean, and you correct me if I'm wrong, is that 6/5 is twice as big as 3/5, right? Right?
Yeah.
It took 2 of them, so that's why you said to add it onto itself. So right. So 3/5 times 2 is 6/5. So if you'd just taken your answer, the 4 2/3, and doubled it, you would get 9 1/3. So sometimes you can find values within the table without doing quite as much work. Okay? All right. Now for number 4, I'm going to do a lot of the work for you because I want to get to the point of number 4, and that's this. So I think we all know that we're supposed to find the unit rate. So in this problem, which makes more sense, ounces per dollar or dollars per ounce? Yeah. So that's what we're going to do to find the unit rate. But like I said, I'm going to do this for you, and it happens to be 70 cents. So the unit rate is 70 cents per ounce. And that would make the constant of proportionality 0.7. Now once again, I'm going to do all the math for you to fill in the table here because I want to get to the important reason for doing this problem. So that would mean for 6 ounces, 6 times the multiplier gives us $4.20. For 8 ounces, that would be $5.60. And for 10 2/5 ounces, that would be $7.28. So if you know the ounces, to find the amount of dollars it would cost, you just multiply by the constant multiplier. But what if I reverse that process? What if I give you $5.25 and I ask you how many ounces you would have based on that same rate? I want you to think about that for a second. And I want you to turn to your shoulder partner and have a very quick conversation about how you think you could find the number of ounces based on $5.25. So what you're looking for is, you know that whatever the ounces are, you're going to multiply it by 0.7 because that's the constant multiplier. So something that I don't know times 0.7, it has to be 5.25. So you could think of that like a one-step equation. 0.7x equals 5.25, divide both sides by 0.7, and then we would get 7 1/2 ounces. So we're going to run into tables eventually, and this is kind of a future knowledge thing. We're going to run into tables eventually where I'm going to give you the other piece, and you're going to have to figure out how to go backwards, like Isaac was saying, because that's basically what we're really doing there. Okay? All right, so could I get all of you to find how many ounces for $11.20? Lucy, what'd you get?
16.
16. How'd you do that?
I did 100, no, sorry, 11.2
Uh-huh.
by 0.7.
Okay. And I'm going to come back to this question right now. So that's right, and 16 is right, and that's how you could go about doing it. But I'm going to come back to this question that I did in the previous problem. Is there a value in the table that you could have used instead of doing it that way? Because sometimes if we look carefully at the numbers that are found within the table, we can get to where we need without doing that stuff. Yeah?
We can multiply the 8 times 2 because 5.6 is half of 11.2.
Yeah, if you double 5.6, right, you get 11.2. So if you double 8, you get 16. So I keep bringing that up now because I want you to be aware of those types of things. Okay, there's always more than one way to solve a problem, always. All right, so we've got 2 problems left, and they both revolve around the idea of what if I give you an entire table. We're going to do number 5 together, and then I'll have you try number 6. Part A, it says, what is the unit rate of cups of flour per cookie? Can I get all of you to find that, please? What is the unit rate of cups of flour per cookie? All right, what is it? Patrick.
$5.50 per cup.
What is the unit rate of cups of flour? Where does money come in? You have the right number.
5 cups.
There we go. All right, 5. Wait, but I think you went backwards, right?
I went backwards too, that's why.
Yeah, we have to read what's going on here. Cups of flour per. I didn't mean to do that. Cups of flour per cookie. So it's this, and I would take one of the ones that doesn't have any decimals involved there. 6 divided by 33 is 2/11. So is 8 divided by 44, and really so is that, and so is this, and so is this, but hunt for the easiest one. So that's 2/11 of a cup of flour per cookie. All right, now based on that, go ahead and answer part B. How many cups of flour would be used for 22 cookies? All right, so tell me, how many cups of flour would be used for 22 cookies? Just tell me, please. 4, good. 2/11 times 22 is 4. Now we're going to flip it. What is the unit rate of cookies per cups of flour? Now, those of you who did part A incorrectly, you already have your answer, right? Tell me what it is.
5.5.
5.5, right. Because now we're going to go 33 divided by 6 or 16.5 divided by 3. All right, so go ahead now and answer part D and part E. And then we'll go on and finish this one off, and then I'll have you do number 6 with your shoulder partner. All right, Fonzie. How many cookies could be made with 15 cups of flour? How many? Is that right? 82.5? It is correct, yes. And then, part E, how many cookies could be made with 0 cups of flour? That's not a trick question. 0, exactly. Okay, so there's a couple of additions on to this table. Before we even get into that, which makes more sense? Cups of flour per cookie or cookies per cup of flour? Now, how many of you have baked cookies before? If you've baked a cookie before, you should know which one makes sense. Because if you have a cookie with more than 1 cup of flour per cookie, probably not going to taste very good, right? Which one? Cups of flour per cookie? Is that right? No, I think it's the second one. Because for 1 cup of flour, you can make quite a few cookies, right? Cookies per cup of flour, that's the one that makes more sense. And so the reason why I'm asking that is because that's the unit rate that's going to be the better unit rate when you are figuring out cups of flour, okay? Or going from cups of flour to cookies. So we know that 1 cup of flour will make 5.5 cookies. And so the constant of proportionality is 5.5. That's our constant multiplier. So if we take the cups of flour and multiply each one by 5.5, we get the number of cookies. Everybody find out how many cups of flour you can make, how many cups of flour you need to make 99 cookies. So this is 3 problems in a row where I'm trying to encourage you to do something. Is there a value in that table that would help you figure that out quickly? Yes or no?
Yes.
Which one? 6 and 33, right? 33 times 3 is 99, so 6 times 3 is 18. Now, if you didn't know that, you could go about doing the equation way, but I want you to continue to look for those values, okay? All right, we're going to finish this up with number 6. Please work on number 6 with your shoulder partner. All right, so we have a bunch of pieces of information from the table. The first part in number A, or letter A, says what is the unit rate of inches per hour? That's 3 inches per hour. I would have taken that piece of information there, but it doesn't matter because what we have within this table, as we've seen this year and as you saw last year, are a bunch of equivalent ratios. They're all equivalent to each other. They will all give you that same unit rate. At this rate, how many inches of snow would have fallen in 3 1/3 hours? Well, of course, that would be 10 inches of snow. 3 inches per hour times 3 1/3, that gives us 10. So now the flip of that was the unit rate in hours per inch. That would be 1/3 of an hour per inch. And that was part of the point in yesterday's homework, was getting you to see that when you flip the unit rate, it's just the reciprocal. Okay? And then at this rate, if there are 6 1/2 inches of snow, how long has it been snowing? That would be 2 1/6 hours. All right. And we are finished for today.